Hello everyone, welcome to the second video on oscillators. We had studied in the last video about LC oscillator and some basic concept of oscillations. Okay, so in this particular video we are going to specifically deal with mathematical analysis of LC oscillators. Let us start. Here is the general form of LC oscillator. You all can see over here there is an amplifier, okay, and there are some impedances which are present over here, Z1, Z2, Z3. Okay. Now, the amplifier can be made up of BJT, it can be made up of FET, it can be made up of op-amps. Now, I have specifically mentioned over here base, collector and emitter, which means we are going to derive it for transistor. We can use anything basically. Okay. Then there are Z1, Z2 and Z3. These are nothing but the reactive elements in the sense they are frequency dependent components, okay, which means L and C. They basically form a part of tank circuit which is going to decide the frequency of oscillation. It's going to generate a sinusoid, right? Which sinusoid it's going to generate, about what will be the frequency of that sinusoid, that is going to be decided by this particular tank circuit. To be specific, Z2 over here is connected back to base, which means it is connected back to input in the sense this is going to be the voltage across this Z2 is going to decide the feedback voltage. Fine. Now in this general form of LC oscillator, we are going to derive some expression. But what are we going to check? We are going to check basically the Barkhausen's criteria. What is Barkhausen's criteria? It is A into beta is equal to 1, which means we are going to find A, we are going to find beta. Okay. And to find out beta, we require feedback voltage and we require output voltage. So these things we are supposed to find out. So what we are going to do is that first step towards this is to replace this amplifier. This is just a box over here, right, with its equivalent circuit. Okay. And what we had studied about the equivalent circuit in EDC1, we had studied RE models and hybrid models. So what we are going to do over here is we are going to make use of hybrid model. Okay, let us have a look at this hybrid model. This is a complete hybrid model, if you can recollect from EDC1, okay, wherein I have HI, HRE V out, HFE IB and 1 upon HOE. Now certain assumptions with respect to LC oscillators I will make over here. First assumption, HRE is very small. If HRE is very small, the product of HRE and V out will be still more smaller. That is the reason I am going to ignore this source. Fine, this is the first assumption. Second assumption I'll make over here is I'll make this HOE very small. So 1 upon very small is very big. So if at all resistance is quite high, current won't flow through that resistor, right? So it is as good as that resistance is acting like a open. So I'm going to ignore 1 upon HOE. That is my second assumption. Okay. Now with these two assumptions, I'm going to remove this. So I'll be just left out with HIE and HFEIB. Okay. So I'm going to replace that amplifier box from previous slide with this circuit. Okay. So you can see over here it is HIE and HFEIB. Okay. Now, as I told you all, A into beta is equal to 1. We are going to verify. Okay, we are going to derive the expression from that, but we need to find A and beta. So to find out beta, we will require VF and V out. So first step towards that is to find out the load impedance between the output terminals 1 and 2. 1 and 2 are the output terminals. How do I come to know? We take output of an amplifier across collector, right? So collector terminal, just have a look. It is collector terminal and other terminal should be emitter, ground, right? Now, to find out the load impedance, what I am doing is that, see, I have to find a load impedance over here, correct? So, I have to solve this particular circuit which is mentioned over here in red box, okay? I need to solve this particular circuit, get the equivalent resistance, and that resistance is going to be parallel with that of Z1, okay? So let me say that the impedance over here in this particular loop, overall impedance, let it be ZL. Now to find ZL, we'll start from here, that is from the base. Okay, so you have, if I solve this particular part, this is just to maintain the symmetry, it is shown in boxes, okay, this particular part and this particular part, but it is as good as Z2 is in parallel with HI, correct? See, this is the same path, okay, so it is as good as Z2 is parallel in HI with HI, okay. Now Z2 parallel with HI will appear in series with that of Z3, okay, because if this is the parallel combination I solve, this same current I1 is going to flow through it, this I1 is same flowing over here, it will flow through Z3 also, okay. So Z2 parallel HI in series with that of Z3 will give me ZL dash, which I have named for this red box over here, impedance in this red box, fine. After finding ZL dash, I'm going to find ZL, which is going to appear in parallel with Z1. Fine. So let us begin. First, I'm going to find out ZL dash. Okay, as I told you, it is Z2 parallel HI, Z2 parallel HI in series with that of Z3. Z2 parallel HI I can solve as Z2 into Z2 into HI upon Z2 plus HI. Okay, now cross multiply this. So you're going to get something over here, okay. Still solve this further, get HI terms together, okay. I'm going to get this. This is my ZL dash, okay. I hope this is clear to you all. Next step is to find out your ZL, which I told you all, Z1 parallel ZL dash. Here was ZL dash and this is your Z1, okay. Solve this. Now, parallel combination I can solve in this way also, that is 1 upon ZL is equal to 1 upon Z1 plus 1 upon ZL dash. The reason why I am not doing Z1 into ZL dash upon Z1 plus ZL dash is that the equation behind is quite huge, okay. So it will become complicated. Too many terms at the numerator, too many terms at the denominator. So what I do is that I follow the traditional method of parallel combination, that is this, okay. There should not be a problem in this. Now substitute ZL dash, whatever things we have got, okay. So it is 1 upon ZL dash, so ulta it will become whatever expression you had got in the previous slide. Cross multiply, okay. Nothing to worry, these are simple steps, okay. Now this is the expression of 1 upon ZL dash, 1 upon ZL. So to get ZL, I will have to invert this expression. So this is the expression over here, okay, which is inverted. I hope this is clear to you all. Now, so impedance I found out. Now next step is to find out A, V out and VF. Why I require V out and VF is to find beta basically, okay. And A is nothing but the gain which I have already found in EDC1, okay. So what I'm going to do is that I'm going to take that expression directly for hybrid models, okay, because you all remember the derivation for the hybrid model itself was a huge thing. So if at all I introduce that, this derivation will become still more bigger, which I don't want to happen. So I'll take that expression, which is anyways very simple, okay, that is minus HFE upon HI into load impedance. So A is equal to minus HFE upon HI into ZL. I'll call that equation 1. Okay. What is the next step? Next step is to find V out. Where do we get output? Output we get across collector. Okay. So to get the output across the collector, okay, what I'll do is that I'll use this strategy. Okay, that is across 1 and 2 terminals. In the previous slides, we have solved this particular part. Okay. So I'm going to use that particular circuit. After solving, I had got what? ZL dash. Now the voltage over here across Z1 is going to be same as that of voltage over ZL dash because they are in parallel, correct? So what I'm going to do is that I'm going to find V out. What is V out? Output voltage is nothing but current multiplied by the resistance. So voltage over here is going to be same as voltage over here. Okay. So voltage over here is going to be V out is equal to current multiplied by the resistance, basically V is equal to IR, okay. So I1 multiplied by ZL dash, okay. But what is ZL dash? We have already found out, ZL dash was Z3 plus Z2 parallel HIE. In the previous slides we have done this, okay, which we had got somewhat this way, right? Z3 plus Z2 parallel HIE is this, right? Okay. Now solve this further, cross multiply, okay, solve this, and you are gonna get some terms over here. Let me call this as equation 2. So this is my V out. Next step is to get Vf, okay. Now to get Vf, it's nothing but with respect to the feedback, and which was the impedance with respect to the feedback? I mentioned earlier it was Z2. Now you don't find Z2 over here somewhere, right? So I'll go back to my previous circuit, okay, wherein Z2 was there, okay. So I need to find voltage across this Z2. Now how to find voltage across this Z2? Okay, it is same as that of, see, this current is flowing over here, right, I1, okay. So the voltage over here, I can find out Vf as this I1 multiplied by the parallel combination of this, okay, will be Vf. It's the same, right, because this is a parallel combination. Voltage over here is going to be same as voltage over here. So the parallel combination is going to give me, because I1 is known to me, so I am going to write Vf is equal to, this is the parallel combination, Z2 HIE upon Z2 plus HIE. This is the parallel combination of Z2 and HIE into I1. Let me call this equation 3. Now what I need to do is that with V out and Vf, I am supposed to find out beta, okay, and beta is Vf by V out. This we had seen earlier also. So Vf upon V out. If I divide this two, this Z2 plus HI is going to get cancelled, and I1 is also going to get cancelled, okay, and finally I'll get this particular expression. Fine. So I'm going to number this equation as equation 4. Now I have A with me, I have beta with me. What I'm supposed to do is apply Barkhausen's criteria. So apply this criterion, A beta is equal to 1. Substitute A is nothing but minus HFE upon HIE into ZL multiplied by, this was my beta over here which I've just got over here now. Fine. Solve this, multiply these terms inside, this HIE and this HIE is going to get cancelled. I'll take this minus over this side. So it's going to be somewhat this way. Now why this term has suddenly become huge? The reason being that ZL I have substituted, okay. ZL is something which we have already derived in the previous slide, okay. So please do substitute ZL, nothing to worry, it is just on substitution, okay. So after substituting ZL, this equation is going to be huge, but not to worry because the terms are going to get cancelled. This term and the denominator of this term is going to get cancelled. HI into Z2 plus Z3 plus Z2 Z3. So what am I going to get after that is this, okay. So it's not so huge. Fine. What I'm going to do now is multiply both the sides by minus 1 and then cross multiply. I'm going to get somewhat this way, minus HFE Z1 Z2, okay, and this particular term. Fine. Bring HFE on this side. See, here there is Z1 Z2, here also there is Z1 Z2. So it will be Z1 Z2 will be common, so it will be 1 plus HFE term which will be left out, okay, and this is my final expression for general equation of oscillator, okay. So this is the general equation for oscillator, not any oscillator, but it is LC oscillator to be specific, okay. Now one by one we are going to consider the types of LC oscillator, okay. So this was the general expression for, or general equation rather, for LC oscillator. Let us start with the first type of LC oscillator, that is Colpitts oscillator. Now Colpitts oscillator, what all things we are going to do under Colpitts oscillator? We are going to see its construction, its working, and finally the mathematical analysis. Fine. Let's start. To understand, first have a look at the Colpitts oscillator. Okay, this is how the Colpitts oscillator look. It has an amplifier and it will have a tank circuit, okay. But to know little bit about a Colpitts oscillator, it can generate a sinusoid with frequency up to 100 megahertz, okay. Up to 100 megahertz it can generate the frequency. Now let's have a look at this. it uses an amplifier circuit over here, okay, which is an inverting amplifier, okay, and it has a phase shift network which has, see, there are two capacitors, one inductor, fine. So it is an LC network basically, fine. Coming back to this particular circuit, okay, let's have a look over here. Here there is R1 and here there is R2, okay, and there is RE in parallel with CE. What this all together form? This R1 and R2 will definitely act like a voltage divider, and RE and CE, we have studied in EDC1, it provides stability to the transistor, okay. So that is the work of this particular components. Construction meaning you are supposed to explain each and every component, what it does basically, okay. Now coming back to the phase shift network, now you have C1 and C2, okay, which also act like a potential divider because the circuit is similar, right? Only capacitors are there over here, okay. So again C2 along with this L, okay, the voltage across C2 basically is fed back to input base, okay, that is VC2 will provide the feedback for sustained oscillations. Now coming to this RFC, that is radio frequency choke, okay, nothing but the inductor, okay. What it will do is that it will allow DC to flow through it, okay, and provide high impedance for AC, okay. Another important thing about this RFC is that whatever energy is stored in this RFC is being capacitively given to this tank circuit, okay. The energy is given to the tank circuit. Now the very fact that you are giving this energy to the tank circuit via CC2, what is the function of CC2? It will pass AC, okay, and block DC, fine. To understand a little bit more, L and C2, the junction meets over here, it is given to base via CC1. The function of CC1 is to pass AC and block DC, okay. Now transistor provides phase shift of 180 degree because it's an inverting amplifier, so it's going to provide phase shift of 180 degree phase shift. It's a common emitter amplifier basically, so it is going to provide the phase shift of 180 degree, and this phase shift network provides a phase shift of another 180 degree. So total phase shift this network or the entire loop provides is 360 degree, which means it satisfies the first Barkhausen's criteria, okay. That is total phase shift of a network is 360 degree. Now let's look at the output. Output is achieved over here, that is at the secondary winding L dash. Now the frequency of oscillation is decided by this tank circuit, okay. And when I say this frequency of oscillation can be varied, okay. And how do I vary this frequency of oscillation? It is done by gang tuning of this capacitors C1 and C2. What do you mean by gang tuning? Gang tuning is something, now say let us consider a potentiometer which we use in labs, okay. That potentiometer, it can be varied, right? It varies the resistance from 0 ohms to say 10 kilo ohms, okay. You can vary it basically. Similarly the capacitances can be varied, but here the capacitances are varied in such a way that the ratio remains constant. Now what do you mean by this? Let us take an example. Listen to this carefully. Let me take C1 as 1 farad, C2 as 2 farad, say for example, okay. What is the ratio? It is 1/2, okay, which is half, okay. Now by gang tuning, say suppose I am varying the capacitances, okay, and by gang tuning, say suppose capacitor C1 has become 2 farad, then automatically this capacitor C2 will become 4 farad in order to maintain the ratio, okay. So what will be the ratio? 2/4, again it will give me 1/2. So the ratio is maintained but the values are changed. Since the values are changed, the frequency of oscillation is also changed, okay. I hope this is clear to you all. Now with this construction is over, coming to working, that is how the oscillations are generated basically, okay. To begin with, let us apply this VCC. The moment you apply this VCC, what's going to happen is that the capacitors C1 and C2 are going to get charged. If capacitor C1 and C2 are going to get charged, what is going to happen is that electrostatic energy is going to get stored. After some time, this electrostatic energy will be given to this inductor, which will be converted into magnetic energy, okay, which will set up the oscillations with desired frequency. Okay. Now what will happen is that, okay, to tell you all, the frequency of oscillation for this particular circuit is given by this particular expression, which we are going to derive later. Fine. Now, the moment this is done, L, C2, which are meeting over here at point 3, are given back to the base by capacitor C1. Okay. So, the oscillations, part of oscillations are given over here back to the amplifier circuit. Now what will happen is that it is going to amplify these oscillations, okay, in order to meet the losses which I had explained you all in video 1. Okay, there are losses. Why the losses happen? It is basically because of the transfer of energy from capacitor to inductor, inductor to capacitor. Remember? Okay, so those losses are compensated now. Fine. Okay, so since the losses are compensated, we will get sustained oscillations and not damped. Okay, the oscillations are not going to get die off. Okay, they are going to be maintained. Fine. So your A beta is equal to unity is also being mentioned for sustained oscillation. This is it with respect to the working of Colpitt's oscillator. Now I'm going to move to the mathematical analysis. Fine. To understand the mathematical analysis, we'll have to consider the general diagram and the Colpitt's oscillator diagram. Okay. Now there is Z1, Z2, Z3. Here there is C1, C2, L. Okay. Now we have to clearly identify what is Z1 for, whether it is for C1 or C2. Okay, that's very important. So look at Z1, it is connected to the collector. Similarly, look at C1, it is connected to the collector, which means Z1 is nothing but C1 over here. Okay. Then similarly, C2 is connected to the base. Just have a look at Z2. Z2 is also connected to the base. So I can say that C2 is Z2. Okay. And Z3 will be definitely your inductor. Fine. Now, from this I can write this expression Z1 is for C1, but I cannot write C1, right? I have to write it in terms of the reactance part of it. Okay, and what is reactance? XC is going to be 1 upon j omega C. So 1 upon j omega C1. Similarly, Z2 is going to be 1 upon j omega C2, and Z3 is going to be j omega L. Fine. I hope this is clear to you all. Now, what we'll have to do is we'll have to take the general equation which we had derived for LC oscillator, and this was the expression, right, we had derived in the previous slides. Okay, I'm going to take that particular expression now, okay, and substitute Z1, Z2 and Z3. Okay, so Z1, Z2 and Z3, let us consider Z1, I have got this, right, but I'll just rearrange this. I'll just take this J on top. It will be minus J upon omega C1. Similarly, Z2 will be 1 upon j omega C2, so minus j omega C2, and Z3 will be just like j omega L. Substitute all these three things over here. What is going to happen over here in this particular expression is that the expression is going to turn out somewhat this way. Nothing to worry again, it is just a matter of calculations. Okay, understanding is more important over here. What you all need to remember is this particular expression, and this you all get it from circuit. Okay, and whenever mathematical analysis is asked, you are supposed to draw the circuit diagram. Fine. Now we'll have a look at this particular expression. HI, Z1 I have substituted, Z2 I have substituted, Z3 I have substituted, plus Z1, this dot signifies multiplication. Okay, Z2 1 plus HFE plus sign, Z2 again, okay, and Z3. Fine. I hope this is clear to you all. Now task is for you all to solve this particular expression. Again, nothing to worry. What you are supposed to do is multiply this term inside. Okay, multiply this and multiply this. Okay, you are going to get three different terms. Then what you're supposed to do is rearrange the terms. Rearrange the terms in the sense you're going to get some real terms, you're going to get some imaginary terms. Okay, so get the real terms and imaginary terms together. Okay, now while solving this, please do remember that j into j is j square, which is equal to -1. Okay, please do substitute that while solving. Fine. So what you are supposed to do is rearrange the term. Rearranging in the sense, arrange it in such a way that you get real terms and imaginary terms just like this. Okay, please don't copy directly this way. I want all the intermediate steps. Fine. So I will get somewhat this way. This is my imaginary term and this is my real term. There is no j term over here, which tells me that it is a real term. Okay, let me call this equation 1. Now from here onwards, what I am supposed to do, I am telling you all in brief. First thing, I am gonna make the imaginary term 0 and get frequency. Second thing, I'm going to put real term and going to get some conditions. Okay, let's start. First, put the imaginary term 0. So I'm going to put this imaginary term 0 over here. It's made 0. This minus j is gone to the other side, so 0. Okay, now hi is not 0, that I know, right? Since hi is not 0, definitely this I'll make it 0. So solve this, take this omega L on the other side. Okay, now solve this, cross multiply. Okay, you're going to get somewhat this way after solving. Now what you're supposed to get from this is this, multiply this. Okay, omega into omega, you'll get omega square L C1 C2 it will be. Okay, this is my omega square. This is the expression I'll require ahead. Then what you all can do is that distribute the denominator after putting the square root, that is omega square is this, right? So omega is going to be square root of this. Okay, and now distribute the denominator. So after distributing the denominator, I'm going to get this. Okay, please do solve this intermediate steps. Okay, now what is omega? It is 2 pi f. So 2 pi f is this. So f is equal to 1 upon 2 pi root of this particular term, which I had made use during the explanation of working of Colpitt's oscillator, if you all remember. Okay, so this is how we get this expression. I'll call this equation 2. Okay, so the part 1 is over, that is imaginary term equal to 0, you get this frequency. Now put real term equal to 0. Okay, so real term was this. Okay, this is my real term. I'll put it 0, rearrange the terms. Fine. What I'm supposed to get from this is HFE. Okay, so try to get HFE from this. Solve. Okay, C2 C2 will get cancelled over here. Okay, solve this. Now over here I have got omega square. I'm going to substitute this omega square which I derived in the previous slide. Okay, so substitute that over here. So what will get cancelled? LC1 will get cancelled. Okay, so you'll be left out with C1 plus C2 upon C2. Distribute the denominator. So you're going to get 1 plus C1 upon C2. Fine. I think this is pretty much clear to you all. Now solve this. I'm going to get HFE is equal to C1 by C2. HFE is nothing but beta. Okay, so nothing to worry. Fine. So loop gain must be greater than unity so that the circuit maintains the oscillations. Okay, if at all you all remember, to start the oscillation I will make A beta greater than 1. Then the circuit is going to adjust by itself to maintain oscillations. A beta is equal to 1. I mean the Barkhausen's criteria. Okay, so let us make use of that. A beta should be greater than equal to 1. From this I will say that A is greater than equal to 1 upon beta. What is beta? Beta I have just got over here, which is going to be 1 upon C1 upon C2, which is going to be C2 by C1. I hope this is clear to you all. With this, the mathematical analysis for Colpitt's oscillator gets over. Okay. Now next is something known as Clapp's oscillator. Now what do you mean by Clapp's oscillator? Clapp's oscillator is just a modification to Colpitt's oscillator. Okay. So what is the modification? Have a look at this circuit. Okay. You have C1, C2 and L. But the extra thing is C3 over here. which means that you just don't have L over here, you have LC3. Fine? L in series with C. Okay, so it's a improvement. Okay, now why this improvement? So what was wrong with Colpitt's oscillator that you require improvement? The thing is that in Colpitt's oscillator there was not frequency stability was not happening properly, okay, because of the stray capacitances basically, okay. So what is done is that you introduce C3, which is going to help in frequency stability, okay. So now you have C1 in parallel with C2 in parallel with C3. All these three are in parallel. So I can write 1 upon C is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. If I solve, I am going to get somewhat this way. Fine. And the frequency of oscillation, no need to derive it again. It is just a modification for the expression of Colpitt's oscillator. This was till here, it was for Colpitt's oscillator. Now the extra term is 1 upon L C3. Okay, that's it. Now what is C3 doing? Okay, what is the modification done over here is you don't vary now C1 and C2 just like how it was done before. You'll remember in Colpitt's oscillator we used to gang tune them and then change it, right, to maintain the ratio basically, okay, and to change the frequency. Now over here C1 and C2 are kept constant, C3 is used for tuning purpose, okay. I hope this is clear to you all why C3 is used. Now C3 which is used is much smaller, so I can, if it is much smaller, the parallel combination will turn out to be approximately equal to C3 itself. So the frequency of oscillation, I can write it as F is equal to 1 upon 2 pi root LC, okay. These terms will disappear, so you will have root of 1 upon LC3, which I can write as 1 upon 2 pi root LC3. Now while taking C3, you need to take care, okay. It shouldn't be so small that the net inductive reactance is just gone, okay. What should happen is that this C3 should be chosen wisely such that it is not very small. If it is very small, what will happen is that circuit will not create any oscillations. Why? The reason being that C1, C2 is also constant, okay. So if at all you are not changing anything, it is as good as circuit will refuse to oscillate. Fine. So why Clapp's oscillator is preferred over Colpitt's oscillator? The reason being that you have C1 and C2 which are being gang tuned, I had told you all, and which are affected by stray capacitances wherein the frequency of oscillations in Colpitt oscillator vary, okay. It suddenly changes, which I don't want to happen, okay. But in Clapp's oscillator, C1 and C2 are kept constant, but C3 is varied, which doesn't have any effect on stray capacitances of the transistor, okay. So the oscillation frequency is stable and accurate, and that is the reason we prefer Clapp's oscillator over Colpitt's oscillator. Fine. Let's have a look at the numerical over here which is present, okay. They have given me the values of L, C1 and C2. I am supposed to find out the frequency of oscillation. Now to find out the frequency of oscillation, it's very simple. Use the expression, okay. Substitute, all the values are given to you all. Please substitute and check whether you all are getting this answer. Fine. Second thing, if the output voltage is 10 volts, find a feedback voltage, okay. They have given me V out as 10 volts, okay. Now this is very important, you all should know. Where we take the output we take across the collector, and across the collector which capacitor is connected, C1 or C2? It is C1, right? So C1 is connected, so that is the reason you have XC1 over here, okay. Current is the same, so VF over here is feedback is decided by capacitor C2, so XC2 over here. Current is the same, that is the reason current gets cancelled and only the reactance part is left over here. What is XC1? 1 upon omega C1. XC2 is 1 upon omega C2. So this will turn out to be C2 by C1. Substitute C2 and C1. Solve this further, okay. And also V0 is given to me. So from that I can easily get my feedback voltage, okay. Now the next question, find the minimum gain if frequency is changed by changing L alone. Okay. Now, so we need to find out gain. What is gain? The last thing which we found out by equating the real part, okay, that is A is equal to C2 by C1. Okay, if at all you'll remember, C2 by C1, it is not dependent on L at all, correct? It is just C2 by C1. So just substitute C2 and C1, check whether you get this, fine. Okay, the next thing which is asked in the problem was find the value for C1 for gain 10. Now gain is varied. Gain was 5 right over here. Now gain is made 10. Okay, if gain is made 10, find the value of C1. C1 is at the denominator side. So C2 by C1, C1 is unknown. So I am going to find C1, which is C2 by 10. Okay, solve this, check whether you all are getting C1 as 50 picofarad. And the last, with this change, you're supposed to find out the frequency of oscillation. So again use the same formula, check whether you all get this. Okay, now C2 will remain the same over here, fine. C2 and L will remain the same, but C1 you're going to take as 50 picofarads. Okay, check whether you all get this. These are problems for practice. You all can just practice these problems. References, I have only used J.B. Gupta. Thank you.